Good afternoon, everybody. How are we all? Clicker. Green button to make it move, I assume? Good, fine. Anyway, I'm Michael Daly. I'm Senior Director of Stuff for Imperva. I call it Stuff because I own InfraEng and SRE and lots of other bits and pieces, but mainly I own the automation team. We're all sat over there. Hello, guys. And so we're here to talk about that. So, I've been in this industry for 30-ish years now. I started out on help desks. I then went on and built networks and dealerships for Mercedes-Benz in the UK. More recently, I've been building out the SRE teams at Cloudflare, then some startups, and the last years I've been at Imperva. The obligatory, this is weird not having a thing behind me, the obligatory Imperva discussion. So we do CWAF, we do DDOS, we do all kinds of security tools and that kind of stuff. We've got 60-something POPs around the world, a little bit over 1,000 network devices, 4,000-ish servers around the network, and we were purchased by Thales in 2023. So we have many systems that make changes on our edge, and they don't all necessarily talk to each other. There's lots of old code in lots of strange languages. There's some Java, there's some PHP, there's some Groovy. Does anybody here still use Groovy for anything? Nope, didn't think so. No modern libraries, and there's very little documentation. The conversation we have regularly around this room, where's the documentation? There isn't any. A lot of it is fire and forget, and no one ever knows if changes were actually successful unless we spend a lot of time looking at it. So, Imperva, which slide are we looking at? Yes, that's better, thank you. Right, so Imperva, we're a rocket ship. Right, we've got this big thing, it's flying through space. It must be pretty good because somebody just spent $3.7 billion buying us. But you know what? It's really old technology, it's a bit broken, and we have to fix it. So, this is my view of how we fix this thing, and a general approach to kind of building software and building automation tools and building things generally. So, 1863 was a really great year for cars because this gentleman was born. This is Henry Royce. Now, he was the youngest of 5 children, but he was absolutely obsessed with engineering. He liked to make things really well. So, with some money from a friend and a bit of a partnership, he started a business making cranes. Now, Royce electric cranes were the best, the very, very best cranes you could buy. Around the turn of the century, we're talking about, late 19th century, early 20th century here. They started to get lots of imports from America, from the French, from the Italians. They were cheaper, but they weren't as good. And they weren't as good because Henry was absolutely obsessed with precision, making everything really, really precise, really, really accurate, making things work really, really well. And precision is key in what we're talking about today. So, let's talk about precision. Actually, let's talk about accuracy, because they're kind of the same thing, or they're kind of not the same thing, and we have to define that in some environment. So this is how I define it. My first job was with Mercedes-Benz. My first proper job was with Mercedes-Benz. If you ask my mother, my first proper job was Mercedes-Benz. And the CEO was a very stereotypical German. Stickler for timekeeping, did not like tardiness at all. So when you joined the board of Mercedes-Benz, you were given this watch. This is the same watch that he has, and it's radio synchronized with Munich. So it always says the same time as his watch. You can never ever be late for a meeting because your watch must say the same time as his watch. Okay, this watch is very, very precise. This is my watch. Now, I love this watch. I've had this watch for 20-something years. My wife bought it for me. Last year, I spent the price of 2 Apple Watches having it completely refurbished. That's how much I love this watch. I'm not going to change it. But when I flew in yesterday, I had to move the hands around myself to make sure it was telling the right time. Every month or so, I have to go and change it because it loses a little bit of time. But I've never missed a plane or a train or an automobile because of this watch. But this watch is only accurate. So, his $1,000 precision engineered watch is precise. My $1,000 precision engineered watch is merely accurate. And that to me is a slight difference. And it's a difference worth noting. So, let's talk about precision. And let's change my page, otherwise I'll be completely lost. So, precision's got quite a long history. But we'll do this briefly because, Scott only gave me half an hour to talk about, and I could talk here till we go out tonight. But, the first, the genuinely sort of agreed father of precision is this man, John Wilkinson. Now, he was obsessed with making things out of iron, right? And his contribution to the story is the creation of a precision boring machine for making cannons. We're going quite a long way back here. 1774, he patented a new method of casting and boring iron guns or cannon. Now, up until this point in history, cannons, guns, anything like that was cast as a hollow tube, right? And then you'd put a tool in it to try and make it kind of straight and flat and the other things. The problem is, you push a tool into a hole that already exists. It tends to follow the hole that's already there, which means the metal varies in thicknesses. Sometimes it kind of breaks through the edges, and so you'd get cannons where the metal was so thin it would explode, or the metal was so thick the cannonballs wouldn't go down them and they'd explode. Got a problem. So, Iron Man's great idea was to take a solid piece of iron, fix it firmly to a bench, and drive a tool into it, actually boring out the hole as he went. Now, this was such an improvement in quality. For decades, they made cannons like this, until they come up with new methods later and new methods of killing people, which we keep inventing today. But this was great. So, the next person to bring into this story is James Watt. Now, James Watt's widely known for his steam engine, and the difference between a steam engine and a steam locomotive should probably be obvious to everybody, but I can talk to you about that later if you like. But he didn't invent the steam engine, but he did make it rather useful. There we go. This is the very first steam engine that was working. It's made by a gentleman called Newcomb, and I can't point to anything, it's weird. So he worked out that what you needed to do to make a steam engine truly efficient was to inject a little bit of cold water into the bottom of the cylinder. So steam would be pushed into the cylinder, push the cylinder up, put a little bit of cold water in the bottom, the steam condenses, the cylinder gets pushed down by gravity. This works really, really efficiently. However, what Watt realized was that you constantly made the cylinder cold. And when you make it cold, it's less efficient because you're always warming it up again. So he put a little cylinder at the bottom where you put the cold water in, connected some valves to it, so the steam would leak into the bottom cylinder, you condense it in there. The effect was the same, it condensed all of the steam, pushed the cylinder down, but the main cylinder stayed hot, so it was much more efficient. So let's go back to Mr. Wilkinson. Now, he wanted to purchase one of these steam engines for his factory, partly for blowing bellows for his furnaces, but partly for turning the machines that made the cannons. Now, he went down and looked at one of these machines in Watt's workshop and was quite stunned to see steam and water and whatever pouring out everywhere. Quite literally, we just leaked steam and power all over the floor. Now, he realized very quickly that a precision bored cylinder was probably the right way to go. So, his next big patent, excuse me, the tea here is terrible. So this is his next invention. So a method of boring out cylinders. So he strapped an iron blank to a thing, he bored it out, he did all the things he was supposed to do. He took the parts down to Watt's workshop, put it in place, slipped a piston into it, and it worked. But this time it didn't leak, which meant it was much more efficient and it worked much better. This is where the start of the Industrial Revolution really happened, because all of a sudden you had a way of powering things in a nice, efficient way. So, let's talk about locks. Now, this gentleman is Joseph Bramah, and he made locks, but this very specific lock. This is the Bramah lock. Now, the lock itself is fascinating, and I could talk about this for ages as well, but I won't, because half an hour. Locks were rather crude at the time. You could pick them very easily. They would just fall apart with a bit of a tug, and generally speaking, they weren't good. But Bramah came up with this lock. It was very difficult to pick. There was a challenge in his shop window in London to say, if you could pick this lock, we'd give you 200 guineas. Now, 200 guineas in today's money would buy you a reasonably spec Mercedes-Benz. So not bad. It took 60 years before somebody successfully picked it. And there's a bit of controversy about how it was actually picked, but again, half an hour won't go into that. The reason we stopped at this point is not really the lock. It's this gentleman. Now, Henry was an engineer, and he was making locks for Bramah. He was an engineer of great renown. He was really, really good at this thing. Now, Bramah had a problem. Around the turn of the 18th century, the political climate in France meant there's a lot of aristocracy running into the UK. The UK, being friendly and welcoming to all foreign peoples, decided they needed to lock up all their families over. So they needed lots of locks, and they wanted Bramah's locks because Bramah's locks were the best locks. So He couldn't make them fast enough. He didn't want to outsource making it because then somebody would steal the idea, so he had to do something else. Henry Maudslay came up with the idea of actually making machines to make the parts, quite literally machine tools. So, this is a screw cutting lathe. Previously, to cut screws, you put a bit of metal in a vise, you sit there and carve it through, and all of a sudden you've got a screw. Always inaccurate, never the same, very difficult to do. That machine, you set up a dial, you set it to the right tolerances, you turn the handle, out pops a screw. Turn it again, out pops a screw, and again and again and again. Pile of screws, all the same. This is a spring winder. Locks contain lots of springs. Well, they did then. I think they may only contain 1 or 2 springs these days. But again, you set the right tension, you wind the handle, out pops a spring, again and again and again. And this is his biggest contribution. This is the Maudslay lathe. Now, lathes have been around for a long time for making bowls and wooden chair legs and that kind of stuff. But Maudslay made it very, very accurate by building it out of iron. He made the tolerances very tight, and he fitted what they call a slide rest. So there's this big screw that goes all the way backwards and forwards across a lathe that moves a cutting blade into and away from the piece of material you want to cut. The slide rest also moved the blade across the face of the material, so you can make lots of different changes. Now, by making it very precise, by fitting gauges, by adding lots of little screws and adjustments, you could make this very, very fine, which means again and again and again you can make the same part. Just by recording the tools, recording the measurements, you can make the same thing over and over again. And Maudslay produced lots of gauges and templates and tests to make sure that everything was done. So what you could do is you could make a load of parts and throw them in a box, and then a less skilled engineer could just pick up a box, take a pile of parts out, make a lock, hand the lock over, off you went. So, we're now making things. So let's talk about automation. It is, of course, why we are here. This is a pulley block. Now, pulley blocks are used on sailing ships, and they enable one person, to move huge sails around by themselves. We all know how pulleys work. The problem is, around that time, they had to make hundreds of thousands of these things. War at France at that period of time was inevitable, and Spain, and the Dutch, and everybody else we could fight if we wanted to. So we had to make lots and lots of them, and they couldn't make them fast enough. So these two gentlemen got together. So Samuel Bentham, who was the chief of the naval dockyards, and Mark Brunel, the infinitely less famous father of Isambard Kingdom Brunel, who you all know from railways and so forth. Now, Mark Brunel knew of Maudslay and approached him with a plan to automate the production process. So, a circular saw could be used as a mortise cutter. Surplus motion from one machine was passed to the next machine. They all had to continue to keep power and synchronicity with each other. Maudslay was known to be a man who could do this. He spent a lot of time the next 6 years putting together a lot of stuff in a pile of brick sheds. So, they ended up with 43 machines inhabiting big brick buildings in the Navy dockyards in Portsmouth, all powered by leather belts, attached to wheels, driven by shafts, connected to Watt steam engine with Iron Mad's precision ball cylinders. So now we've got precision engineering, driving things, making things, automating things. Cool, so let's go back to where we were. 1863 was a great year for cars, because Henry Ford was also born in that year, just a few months either side of Henry Royce. Can't remember which way right now. Now, he was brought up in Michigan, he was the son of a farmer. He got really into engineering by fixing threshing machines and basic tractors and doing all those kind of things. Now, around 1907-ish, he started to get into cars and decided, I'm going to build a car that everybody can own. He wanted to build a cheap car that people with a decent salary could drive, but it wouldn't be made out of basic materials. It would be built really, really well. Large enough to carry a family, small enough for an individual to run and care for. Around this time, Henry Royce, is a wealthy industrialist, and he's starting to get a passion for cars as well. 1902, he purchased this. This is his first car of sorts. It's a French-made Dion Boutron quadricycle. Essentially, it's two bikes bolted together with a little engine in the middle. He liked them. He thought they were much better than the American machines being made. But, you know, it was good enough. He quite enjoyed it. In 1903, Royce purchased his first true car. This is a 10 horsepower car with 2 cylinders. And now he enjoyed driving it, he loved it, but it overheated, it didn't accelerate well. It wasn't very reliable. And he basically took this car apart in his workshop and re-engineered everything. Nothing was too small to be fettled and improved, no imperfection too minor to be adjusted. He improved the car almost beyond recognition. Now, this work became the foundation for the first car under his name. This is the Royce 10. The Royce 10 was a work of love and passion. He tested it and tested it. He replaced parts. He added drive shafts instead of chains. He developed the brakes. He improved the steering. And one of his engineers once said, no wear or frettage was too trivial for him to notice or make efforts to correct. Now, Royce made several variations of this car over the years. He eventually teamed up with this man, Charles Rolls, and the rest is history. Now, this is the real landmark in Rolls-Royce history. This is the 4050, produced around 1907, and this particular chassis was painted silver, and it ran up and down the country in a kind of demo. Backwards and forwards to Scotland, backwards and forwards. After about 3,000 miles, it was tested and checked and serviced. Nothing was really wrong, so it just kept on going. This thing broke record after record after record. And for the time, that's quite amazing. This is the same vehicle 100 years later. The wheels are different because rubber decays. The leather in the seats is different because leather decays. The rest of the car is the same. It's the same chassis, it's the same pistons, it's the same engine, it's everything. That's how well that car was built. It's running 100 years later. So around this time, Mr. Ford was also getting interested in cars, but far from fixing somebody else's quadricycle, he just built his own. He got a pile of parts in his workshop, he figured out how to do it, he built his own car. Now this is the first car he sold. This is the Model A. Simple car, no fuss, no luxury, just work. With the Model T, this is where Ford really changed the ballpark. Why he went from A to T, we don't really know. There was like 5 cars in the middle, not 18, who knows? But the first T was born on October 1st, 1908. 16.5 million had been built when the last one rolled off the production line. And production line is the key word we're using here. So while Royce was obsessed with perfection, Ford was obsessed in production. When you build a Rolls-Royce, a bunch of engineers in different parts of the factory build various parts for this car, and they take them all into one room, and they try and put them together, and they never fit. So they file them, and they fettle them, and they polish them, and they bend them, and they shape them, and eventually you've got a Rolls-Royce. And this car is a Rolls-Royce, and it rolls out, and it's a Rolls-Royce. It's great. In a Ford factory, everything is delivered ready to go. It's fit for purpose, precisely engineered to exacting tolerances, and it just fits. A workman reaches into a bin, he pulls out a part, he puts it in the car, rolls on to the next station. Everything is interchangeable, everything works. We have a production line. Rolls' cars are accurate, Ford's are precise. So, here's the thing, and this is the thing we've all been waiting for. Here's the big bit. Every company I have ever worked for, Cloudflare, Nominet, Mercedes-Benz, Imperva, all of us, we all build cars. We all build our software like people build Rolls-Royces. A developer over here starts up a text editor and he taps away for God knows how long. Sorry. Taps away for a while, and all of a sudden you've got this beautifully crafted piece of hardware. He picks it up and he carries it down the hall, and he gives it to an SRE and goes, can you do what you do with that? And they go, yeah, and they go, oh, well, you haven't. Oh. Okay, so we need to plug in automation, so we need to rewrite this bit, and we need to, it needs deployment. And eventually, after a while, you've got a Rolls-Royce running out the door. It's going to be lovely. It's going to have a beautiful walnut dashboard. It's going to drive terrifically. It's going to be lovely. It's going to be an absolutely wonderful car. But actually, what we need to do is we need to build Mustangs. We need to be able to roll our software down a production line, pick out the automation piece and plug it in, pick out the monitoring piece, plug it in, just rolls out. Nobody has to worry about it. So, I came to my team with this idea 2-ish years ago about how I wanted to build software. Bearing in mind, I'm not a software engineer by trade, I'm a network engineer by trade. And not a very good one, if I have to say. But anyway, but they liked this idea, and the rest of the company kind of got behind it, and so we're starting to move things forward. But this is how we do it. So every tool uses standard connections. Using the same idea as Steve Jobs, we have APIs for everything. There's going to be no backdoors. There's nothing going on behind the scenes. If you want to get data from one system, you have to go through an API. Every component will do one thing. So if something's sucking data from somewhere and putting it in an engine, putting it in a database or some sort of system of record, Right, it's not going to munge the data. We've got another tool over here that munges the data. It keeps everything simple. We can make one code change over here. It doesn't affect everything else, which is what happens currently in the environment. We will only have one system that makes changes at the edge. So we use SaltStack. We have a network to code. Hello guys. Helps us build a Kafka engine, so we can send commands via Kafka into Salt. Salt makes changes at the end, feeds back data, store it in a database somewhere. We've suddenly got data. Services have single responsibilities. I've kind of already said that. And the new code that we're building is rigorously enforced with standards. The team, I love them. I lucked into a really great team in this job. They get it and they understand it, and they build templates and they build gauges and they build tests and they build, standards that they all work to, and all the code is coming out in a way that makes it feel really good. Makes it easy to work with, which means they can take one bit, give it to another person, they can read it, understand it, document it, move on. So, thank you very much for listening. I'm happy to give anybody the slides if they want them later, that's fine. And time for questions, I think.
Everything you said makes sense. Can you give, maybe just to solidify it, a concrete example of something that was done not following those principles and how it was changed to follow those principles? So kind of don't do it this way because of these problems. Do it that way.
So we've got a lot of bits and pieces in our infrastructure. So let's go back to a previous employer, right? Because that'll be I can talk about it.
It's safer that we talk about a previous employer.
Slightly more abstract in that way. So there was a system at one of my previous companies where we'd take a bunch of data, right, and then we'd do work on it, and we'd figure out what to do with it, and we'd put it in a database, right? But every time you tried to change some of the parameters, you'd have to go and rewrite half the code because it was all in one place. And we had one tool that did 4, 5, 6, 7, 10, maybe different things with this data. We'd take DNS data and munge it in a particular way and link it to accounts and do all kinds of other stuff, and we'd end up with this mess. You change one parameter, and that parameter was used by 3 different parts of the program, and it would just cause a mess. Whereas now, what we're trying to do is we take in like a pile of a company account of a customer's accounts information, right? We store it, we turn it into the code we need to put to the edge in another tool. So we just do it in steps rather than doing it all in one place. We do it in steps. So it becomes that workflow. And the idea is the team is small. Imperva is quite a large company, considering very few people have heard of it. It's a massive organization. We're a bottleneck. The automation team is a bottleneck for features, for products, for everything else. The aim is to get to a point where the developers just pick up the automation piece, plug it in, right, and then they can run it down the thing. And if they want to make changes to the code, great. We treat it like it's open source, so other people can pull requests into it. They can make changes if they want to. We check them, we work on them, we make sure they're okay, keep them within principles and move forward.
Makes sense. Thanks.
Hi.
Hello.
That was awesome, thank you. Can we think of this conceptually as a reframing of the pets versus cattle analogy that's ubiquitous in the industry, or are you thinking of it as something else?
I hadn't thought of it like that, but it certainly helps us start to think of things as cattle rather than pets, because everything is it's another thing that just kind of flows down a production line. We're not looking at it like it's our Lovejoy, and we're not crafting everything individually and making it all special. It's disposable.
Awesome, thank you.
Hi, that was great. This new approach seems like it's going to lend itself well to the agentic approach where AI has discrete tools. Mm-hmm. Just curious, is that sort of in your long-term vision, an agentic approach?
When we started this, it wasn't, but it is now.
Good afternoon. Over here.
Oh, over there.
I'm David with Lebanon Systems. Quick question. How many people do you have on your team actively working on this?
They're all over there.
So, 8?
8.
7?
Sorry. Yeah, 8, that's it. Terrific. I think if I go, I'm a little bit ahead of time, then maybe we get the next one done. All right, one more.
Just quickly, how was the lock picked?
Sorry, I can't.
How was the lock picked? In your slide, you mentioned the lock that was invented
Oh,
and the prize to pick.
the theory is it was taken to pieces. Because the person that picked it insisted on doing it sheltered and in privacy. And over 14 days, the general idea is they took it apart.
So reverse engineered?
Reversed engineered it, yeah. Terrific. Thank you very much for your time. Have a great conference.